Hello everybody and welcome to part 2 of this video series. In this part, I'm going to be explaining to you the theory behind blockchain technology, so specifically going through some key terms like private keys, public keys, cryptographic hash functions, what those are, how those work. I will talk about transactions, how a transaction is created and signed and secured. I will talk to you about blocks, how blocks are connected together. I will then start talking about proof of work, which involves miners and securing the blockchain. And while all of this is very, very interesting, and I try my best to break it down as simply as possible for you in this video. So in a second, we're going to hop over to the drawing tablet. I'm just going to start doing some diagramming and explaining, and I encourage you to sit back, relax, and enjoy the explanation. However, before we do that, I quickly need to thank the sponsor of this video and this series, which is Cartesi. Now, Cartesi is a company that is dedicated to making the blockchain more accessible and affordable. And when I say affordable, the reason that's important is because, as you're going to see as we go through the rest of these videos here, deploying smart contracts is very, very expensive. Now, Cartesi offers a bunch of solutions that can actually cut this cost by a factor of almost 100 and really just make it much easier to work on the blockchain. Anyways, we'll hear more from them later on, and we'll actually start using some Cartesi technology, hopefully in a future series. But regardless, they are an awesome company. They've been helping me come up with the content for this video, and I'm just super grateful and happy to be working with them. Regardless, let's dive into the video. Alright, so I'm now on the blackboard. Ignore the black screen. There will be some drawing in 1 second. But for now, I'm going to start by explaining to you some key terminology related to cryptocurrency, specifically private key, public key, and address. So let's actually start by looking at what's known as a cryptographic hash function, because it's very important to understand this concept. So we have a function, let's say f of x, and this is equal to y. This means you take some input x, you get some output y, pretty standard. Now, with most regular functions, you can compute what's known as the inverse. Now, the inverse of f is known as f inverse, and then you would take y, and this would give you x. So the idea here is that given some output, and given the function that computed that output, tell me what the input to that function would need to be to get that output. So the inverse is like this. You take the output, you pass that to the inverse function, and it gives you the input required to pass to the original function to get that output. So let's just look at one concrete example. Let's say we have something like y is equal to x plus 2. Well, if 2 is my input, then y is 4. Now compute the inverse of this function. The inverse of this function you simply compute by isolating x. So you would just say y minus 2 is equal to x. That's the inverse. And so if I give you the value 4, you can tell me 2 was used to compute that. Great, so now that we understand what the inverse is, the first property of a cryptographic hash function is that it has no inverse. So we're going to call this now the hash function. So let's do hash func. This is going to be our input, and this is going to be our hash, otherwise known as a digest, okay? You don't really need to know that, but hash is what I'm probably going to be referring to this as we go through this video. So the first factor, or the first property of a cryptographic hash function, is that it has no inverse. Now what that really means is that given y, you cannot find x. So if you're given the function and the output of the function, there's no way to figure out what the input is. That's very, very important. So to clarify here, when I say we can't find the inverse of a cryptographic hash, that's not necessarily true. Now it's important to note that here I'm not talking about the cryptographic hash function, I'm talking about the actual hash itself that was the output of this function. So currently, there's no efficient way or formula that we know that we can use to take an individual hash and determine its inverse. However, it may be possible to invert a hash using a brute force approach where you would blindly guess and try several different values until you determine what the original input value was that generated this hash. Now, this brute force approach would take billions of years to perform, and that's why we say a cryptographic hash has no inverse, because it would take an extremely long and unfeasible amount of time to compute it. So yes, theoretically, it may be possible to compute the inverse of an individual hash, but it would take such a long time that we just simplify things by saying it has no inverse. So moving on, the next property of a cryptographic hash function is that it is deterministic. That means that any input x1 always leads to one output y1. So second property, deterministic, again, meaning that one input always points to the exact same output. Next property is that every output is unique. So if I pass x1, I get y1. Nothing else points to y1. So if I have x2, it's not possible for me to get the same y1. As soon as I have something like x2 and they both point to the same output, this is no longer a cryptographic hash function. So again, I need to add a small clarification here. Theoretically, it is possible to have two inputs mapped to the same output using a hash function. Now, when that happens, this is known as a collision. Now, the thing with cryptographic hash functions is that for that to happen, for you to find a collision, just like finding the inverse, that would take you, say, billions of years, a very, very long time to do. So we can kind of operate on the assumption that there will be no collisions, but theoretically, if we're talking about the exact definition, there could be. So I'm going to kind of be speaking in this video in definitives. Just understand there is some nuance behind those, but it's just much easier to operate under these assumptions. And well, hopefully that makes sense. Okay, so those are the first three properties of this function. The next is that the hash that you get is uncorrelated to the input. So what this means is that if I have something like f of 1, 1, maybe this gives me a hash of a, b, c, 2, 3. Now, you might be trying to guess here that if I had a hash of 1, 2, that it would give me something similar to this. Maybe you would think we get A, B, C, 2, 4, or something along those lines, because you would imagine that the output here is correlated to the input. But with a cryptographic hash function, this is not the case. If I were to pass 1, 2, so just one number is different, I get a completely different hash. So I might get something like D, F, A, 2, 9, 4, or 7, or whatever. You know what I mean? We just get a completely different hash. There's no way to reasonably guess what the hash is going to be by looking at the input. All right, so that is great. The very last property is that this is quick to compute. So computing the hash of some input is very, very fast. Those are the 5 properties of a cryptographic hash function. Okay, so moving forward, we're now going to talk about private keys, public keys, and addresses. So let's start with our private key. Now, the private key I like to think of as the master password for our Ethereum account. So the private key is actually what allows us to access our account and to send money. So if you have access to a private key, you have access to an Ethereum account, and well, you can send money on that account. That means you need to keep this private. You do not want to share this with anyone. And in fact, we don't even look at what our private key is. When we use MetaMask, it's generated for us and stored in an encrypted fashion in kind of the back end of MetaMask so that no one can actually see it. Now, when I say encrypted, this is actually one of the reasons why we need to pass a password when we created our MetaMask account. So what happens in MetaMask is it will generate a private key for us, but it won't store it in plain text. So if the private key was 1, 2, 3, it will never store 1, 2, 3. Instead, it will store what's known as an encryption or an encrypted version of this private key. And it will encrypt it using our password. So we have some special function that's going to take in our private key and our password, and then it will give us some output, okay? And then the only way to go from this output back to what this private key is to know what the password is, okay? So we need to use the password every time we sign in so that we can decrypt our private key so that we can then use the private key to actually send transactions. Okay, that is the private key. And what the private key actually is just a string of characters. That's really all it is. It's extremely long. And again, you usually are not going to be looking at this yourself. It's going to be stored in some secure way. So next, from our private key, we generate what's known as a public key. Now, the public key is generated from the private key. So you need the private key to get to the public key, and we use a cryptographic hash function to generate this, which means if you know the public key, there is no way to go back to the private key. You cannot do that because the way we generated it was using a cryptographic hash function. That's very important because someone could theoretically figure out your public key. If they do figure out what that is, that doesn't matter. There's no way for them to go to the private key. Hence why this is private and this is public. The public one can be shared anywhere. Okay, moving forward, the next thing we have is our address. Now, the address is generated from the public key. So a private key and a public key actually make up an Ethereum account, and then the address is what you're going to actually send money to. Now, what the address is actually a few characters. When I say a few, it's something like 20 characters of the hash of this public key. That's pretty much all I will say. It's kind of just a simplified version of the public key. And the way you get the address is you generate it from the public key. So you go private key, address, and from the public key, again, you cannot get back to the private key. From the address, you cannot get back to the private key. And that's very important because as soon as you have the private key, you have access to the Ethereum account. So you give the address to whoever you want to send money to you, and that is how you will reference your account on the Ethereum network by this address. Great. So the whole point of the address, as I was saying, is it's just a simplified version of the public key. So it's a little bit easier to be using on the blockchain rather than writing the public key everywhere. So now that we understand private key, public key, and address, we need to talk about transactions and then how the blockchain actually handles transactions. So let's say we have the example where we have maybe account 1 and account 2, and account 1 wants to send some Ethereum, maybe 0.1 ETH, to account 2. How do we do this? Well, to do this, we need a transaction. Now, anyone can create transactions on the blockchain. Anyone can do it. And what's involved in a transaction is an amount. So this is going to be 0.1 ETH. We're going to have a to wallet. So what address we're going to. So we're going to be going to account 2. And then from, this is going to be account 1. Now, the only problem right now with this transaction is that we kind of have to trust that who's making this transaction is the person who's sending the money, right? The from address. But theoretically, account 2 could make this transaction and say, oh yeah, account 1 is sending me all of its Ethereum. Anyone could just make a transaction, and you could add as many as you want, and you could just throw them on the blockchain. And well, if there was no security, then you would just have random people adding transactions all of the time. That is why we have something known as a digital signature. So a digital signature is a very special hash that involves the actual private key of the account trying to send the money, so of the from account, as well as all the information associated with the transaction. Now, I won't talk too much about the signature because it's pretty mathematically complicated, but to be able to actually create a transaction that is valid, what you need is the private key of the account you're trying to send Ethereum from. So this signature here, again, as I was saying, is going to require the private key, as well as the transaction itself. So the transaction I'm just going to represent by TX. And then there's actually another part of this as well. And anyways, you hash all of this. It gives you some, random string of characters. And this string of characters you can verify is a correct signature for this transaction. Now, the way that you actually verify this signature is simply by using the public key of the account that's sending this Ethereum. So if we see a transaction that's coming from account number 1, we don't need to know account number 1's private key to determine that the signature is valid. We can just use their public key and a special kind of mathematical computation to determine that this signature is valid and that it was actually signed by the account that's sending the Ethereum. Because again, you can only send this Ethereum if you have access to the private key of the account that's supposed to be sending the Ethereum. So just know for now that you can verify a signature very easily without knowing the private key of the account. You just use a certain aspect of the public key. I'm not going to go into too much more detail, but that is how you verify a signature. So anyways, that is how you actually secure a transaction. You digitally sign it using your private key and a few other things. We don't have to manually do that ourselves. It's done by MetaMask when we actually send a transaction. Okay, so let's remove all of this. And now let's see how we actually associate a transaction with a block and how we actually, use the blockchain and put a transaction on the blockchain. Because right now we made this transaction, that's fine, but we need to send it on the blockchain. We need to attach it to a block before it's actually going to go through, before our money gets sent to the other person. So let's look at what a blockchain is. Let's say we have one block like this, another block like this, and a third block like this. Now, all of these blocks are connected together in a chain. Now, they would be of equal size. I've obviously drawn mine a little wonky here, but all of these blocks contain some information on them, as well as all of the transactions and smart contracts that were added to them at the current point in time. So what this blockchain actually does is it represents a digital ledger of the entire history of the Ethereum network when we're talking about Ethereum here, right? So every single transaction is a transaction that has taken place, and we know the order in which they took place because they're ordered on the block, and then all of these blocks are ordered. And this is very similar to something like a ledger that you would have at a bank. So a bank would keep track of every single transaction you had sent and everyone else had sent. It would know all of that information. Well, same thing here with the blockchain. We just do it in a different way. Now, one of the key properties of the blockchain is that it is decentralized. This means it is not controlled by a bank, is not controlled by a single person. It is controlled by a network of computers that are owned privately by random people around the internet. And the reason why this is important is because as soon as something is owned centrally, so by one person or one organization or one entity, they have the ability and the power to do something with it that is corrupt or that is malicious or that anyone else just doesn't have the ability to do, or that they shouldn't maybe have the ability to do. For example, if you own a bank account, the likelihood this is going to happen is very slim, but theoretically, the government could just force the bank to hand over all of your funds. Maybe you need to pay your taxes or something, whatever. The idea is there's a central organization that controls this, and so at any point in time, this central authority could go in and actually modify what's on the ledger. They could change the account balance. They could take money from you. But here, when we're talking about a blockchain, that is actually not possible because this is not owned by one person or one entity. It is used and controlled by all of the computers around the world that contribute to the network. And we'll talk about what those are in a second. But to be able to do anything malicious on the blockchain, you would have to control almost all of the computers around the world that are storing a copy of the blockchain and that are on the blockchain network. Okay, hopefully this makes a tiny bit of sense, but let's have a look at one individual block, kind of see how that works in the context of transactions, and then we'll talk about proof of work and a bunch of other very important aspects of the security of the blockchain. So let's say we have a single block, okay? We can just call this something like block number 2, okay? Now, the reason why I'm naming it number 2 and not number 1 is because the first block in a blockchain is a special block, contains some configuration and initialization related stuff because, well, it's the very first block. So that's kind of a special one. We're going to ignore block 1 for now and just move straight to block 2. Now, block 2 is going to contain some transactions on it. The transactions I'm going to represent by these squiggly lines. Now, these transactions are exactly what I showed you before. They have a to address, a from address, an amount, a signature, and they have a few other things as well. In fact, every time you send a transaction, you usually have to pay a very small fee, and this fee will be given to the miners that are trying to secure and validate a block. Anyways, this block has some transactions on it. Now, this is where we get into the concept of miners. So miners are computers that are sitting around the world that are supporting the Ethereum network. They're actually what allow it to run, and they're what secure the blocks and make sure that you can't just hack the network, okay? So we'll dive into miners in a second. I just want to take a quick step back here. So whenever you're sending a transaction, you need this transaction to be associated with a block, and this block has to be mined, which we'll discuss in a minute, before your transaction actually goes through and is completely successful. Up until that point, your transaction will be pending, but once it's been added to a block and that block has been mined, then it is successful. Now, a new block is added to the Ethereum network approximately every 15 seconds, so very, very quickly. Anyways, now let's talk about mining. So, what are miners? Well, as I discussed, miners are just computers that are sitting around the world. This is going to be my computer, just a bunch of kind of deformed squares here, right? So there's a bunch of these guys sitting all around the world connected to the Ethereum blockchain. Now, every single time a new block is created and all of the transactions are added, it gets sent to every single miner. So all these miners are kind of nodes on the network. They're all sitting there waiting for transactions to get added to the current block. When this happens, what these miners do is try to mine the block. Now, mining the block consists of performing some computations, particularly some very difficult computations that are very time-consuming, and trying to guess a number that makes the hash of a block, which we're going to get to in a minute, have some specific properties. Now, the point of doing this for these miners is that if they are able to guess a specific number, they successfully mine the block and they will be given a reward. So let's say miner 1 actually guesses what the number is. I'll discuss what that number is in a second, and they will be given some reward. Now, this reward will be made up of two things. The first thing it will be made up of is a block reward. Now, a block reward is a reward that is hard-coded into the Ethereum network and actually decreases over time, and this is new Ethereum that will be created and given to the miner as a reward for mining this block. I'm not sure what the current block reward is right now. It's probably something like 1 Ethereum, but the point is that this is new Ethereum that then gets added to the ecosystem and is circulating around. So yes, some cryptocurrencies, and here specifically Ethereum, do have an inflationary aspect to them because new currency is being created, but it's not something you really need to be worried about. And while there's a whole field of cryptocurrency called tokenomics that kind of discusses this and why this is maybe actually a good thing, I'm not really going to get into this in this video. Point being, don't be too worried about the fact that new Ethereum is being created. So the second thing that you're going to have is going to be your fees. Now, every time you send a transaction, you're going to pay a very small fee. This fee goes to the miners that are mining the block. And so the successful miner, the miner that actually guesses the number that mines the block, is going to get the block reward and any fees associated with all of the transactions on the block. Okay, hopefully that makes sense. I'm just trying to explain the incentive structure here for people to actually mine. So continuing, now we need to talk about what the miners are actually doing. What the miners are doing are trying to guess a number that gets added at the end of the block. So I'm going to say num equals question mark that makes the hash of this block equal to a certain number. So what they're trying to do here is they are trying to find some number that they can add as kind of a dummy transaction at the very end of the block, so that when I take a hash of this entire block, so I run this through a cryptographic hash function, the hash that I get starts with a certain number of zeros. I believe right now what they're trying to find is a number that starts with 30 zeros, but it could be actually higher or lower. I'm not sure what the exact number is. The point is that what these miners are going to be doing is trying to guess some number, right? This is a random number that you add at the end of the block. And then when you hash the entire block, so all of the transactions associated with the block and the number together, it gives you some hash, some digest, right, that has 30 numbers at the beginning, or 30 zeros at the beginning, sorry. And then the rest of it doesn't really matter what that is, but you're just trying to find something that has a certain number of leading zeros. So the point of this is that the more zeros that you have in that number you're trying to guess, the harder it is to guess that number, because the probability just decreases that you're going to guess the correct number right here. And again, I'm just really trying to reiterate here that what's going to happen is you're going to take a hash of all of this, everything inside of the block, including this number. And then you want it to give you some number that starts with 30 zeros. But the thing is, there's no way to figure out what this number is other than just guessing and checking, because the cryptographic hash function has that property that there's no known inverse. So since we can't compute the inverse, we have no better way of finding out what this number is other than guessing and checking. And so these miners are just guessing and checking as quickly as they possibly can, and the one that gets the correct number then adds that to the block, that mines the block, and then we create a new block and continue moving forward. Now, this is an oversimplification, but that's the general idea of what these miners are doing. Okay, so hopefully that kind of makes sense, but that is what these miners are attempting to do. And you might be wondering, well, there's so many miners, so is it only actually one miner that's guessing this number? And the answer is yes. At every single block, you're only having one miner that is going to guess what the correct number is and get the reward. That's why you'll have pool mining, which means you'll have like hundreds of thousands of computers that will split their processing power. They'll say, okay, we're all going to try to guess a number together. And if any of us get the number, we're going to split the rewards between everyone, because the probability that one of us can guess the number consistently is very, very low. In fact, if you only had one computer mining and it was not mining very quickly, your probability of ever getting a block reward would be almost zero, because there are just so many other computers doing it, and you would have to get extremely, extremely lucky. So that's why you would mine with a bunch of other people, so that your probability of getting a reward is much higher, and then you would split that based on how much work all of you have done. Okay, so let's continue here. Now what I want to do is draw a few blocks, and we'll see how these are connected and kind of the security aspect of this. So let's just paste this block over here, and for now we can just go with 2 blocks. Okay, so we have block 2, and then this guy is going to have to be block 3. Let's fix your corner right there. Okay, so we have block 2, and we have block 3. Now this would be coming from block 1. We don't need to worry about that right now. Now the thing is, these blocks are connected together, right? So we have block 3, we have block 2. Block 3 is connected to block 2, and obviously it comes after block 2. Now, how do we know that? Well, obviously these arrows aren't actually there. We don't really have arrows connecting these things, but what we do have is a field in every single block that represents the hash of the last block. So we have something like last is equal to, and then whatever the hash of this block is, including the number that we guessed, that is what we put right here to represent this is the last block in the chain. So let's say when we hash all of this, we get a number that is 0000049AB. Now this will usually be a hexadecimal number that is 64 characters long, but for simplicity, we'll just go with this for now. So to get this hash, we would also have guessed this number, let's just say it's 7, and what we were trying to do was to get a hash that started with 4 zeros, which we've done. So next, what we'll do is we'll write this hash here, so 0000049AB. So now in block 3, we know the previous block was block 2, and block 2 would also have this field that would say last is equal to the hash of whatever block 1 is. So now block 3, we get a bunch of transactions on here, we add them all on, and we say, okay, we want to mine block 3. So what we need to do now when we mine block 3 is we have to find some number such that when we hash all of this, including this last field, right, that's going to be included in the block what we're hashing, we get a number that starts with 4 zeros. So what this really means here is that if the hash of block 2 ever changes for some reason, then this is no longer going to be correct. because this is going to be referencing block 2, which now no longer exists. And so this will be disconnected from the blockchain. You can kind of imagine that this arrow would get erased. Now I'll continue explaining this, but again, what we're doing is we're trying to mine block 3. So we'll guess some number. Let's say we guess some number 9, and then we end up getting some hash here. I guess I can just do it in maybe a purple color, 0, 0, 0, and then maybe this is 7, 9, BA, okay? This is the hash that we end up getting. So now, where the real security feature of the blockchain comes in is that let's say I am a malicious entity here, and I want to change one of the transactions on the blockchain. So let's say I take my copy of the blockchain, and I go to block 2, and I change the transaction. And instead, I add this fraudulent transaction right here. Well, as soon as I change this transaction, this hash here changes, right? And the reason this is going to change is because when I take the hash of this block, now since this transaction has changed, I get something completely different. And so what I'm probably going to end up getting here is something that doesn't start with 4 zeros. So say maybe I get 102 ABBC1. That's my hash. So now since this hash doesn't start with 4 zeros, I need to recompute this number and remine this entire block because now the number 7 is no longer correct to give me a hash that starts with 4 zeros. So let's say I'm successful in doing that. And I guess, the number, let's go 275 or something. And now I get a hash like 0, 0, 0, 0, 1, 2, 3, 4. Okay, that's my new hash. Well, now the problem is this hash does not match this hash right here. And so this block is disconnected from this block. And so if I want to actually keep this fraudulent transaction in block 2, what I need to do now is modify block 3 because I have to change this last to match what my new last on block 2 is. So what I do now is I come here and I would need to change this now to whatever this is. So 0, 0, 0, 0, 1, 2, 3, 4. But now that I've changed this, the hash here is going to be completely different, right? Because we're going to get a different value when we have something different inside of the block. So now I get a hash maybe that doesn't start with zeros, right? 1, 0, 0, 2, 3, A, B, C, whatever, some random hash. So now I need to recompute this block, recompute this random number, and remine it so that I now find a hash that starts with 4 zeros. And you get the point. I have to do that for every single block in the blockchain, right? Because these blocks are connected together. And as soon as these blocks are no longer connected, I don't have a valid blockchain. And if I try to send this on the Ethereum network, all of the other computers on the network are going to be like, no, that is not correct. Your blocks are not connected. Your hashes are all messed up. And I have a different version than you have. So no, I'm not going to accept that as a transaction. I'm not going to accept that as a block because that is fraudulent. So hopefully this makes a bit of sense, but this is a concept known of hashes of hashes or hashing of hashes. And so what we're doing is we're taking a hash of this block, putting it inside of here, and then taking a hash of this block that contains the hash of the previous block. And so any change to the previous block means that this will no longer be valid. And so we have to change pretty well every single block in the blockchain to be able to modify everything. And that is why this is so secure. And that is what leads me to the concept of proof of work. So what we're doing when we're mining is we are proving that we have spent a certain amount of time before adding this block to the blockchain. And the reason that's important is because the more time we spend, the harder it is to modify the blockchain. If you had an absolute supercomputer and you could just remine these blocks instantly, then you would be able to go and change the blockchain. That would be fine. You could do that because you could just regenerate every single block with all of your fraudulent transactions added. However, since that's pretty well impossible and we have so many computers working on the blockchain at the exact same time, for you to be able to do that, you would need more computing power than all of the other computers on the blockchain combined, and you would need to be able to not only rewrite the entire blockchain previously to what it's currently at, you would also need to be able to catch up to all of the other computers that are working on the new blocks being added to the chain and kind of beat them. You'd be like racing against them in a sense. I'm sure this is very abstract, but this is what makes the blockchain so secure. That these blocks are actually linked together. You need to perform this mining process, which is proving you've done a certain amount of work. This work takes some amount of time. This amount of time you can calculate using probability, the probability you're going to guess a random number and how quickly you can guess random numbers and all of that. And as the blockchain continues to grow, being able to potentially modify it becomes harder and harder and harder. So anything that is added to the blockchain is pretty well permanent and you cannot remove it without having to rewrite the entire blockchain. So this is all great, but one other thing I will mention here is that another security feature that's built in is that every single computer that is mining the blockchain or mining the current block has a copy of the existing blockchain. And so what that means is that if you try to change something on, say, the current block, every single other computer knows what the current block looks like. And so if you're submitting a block that looks different from that, it's going to be able to tell that very, very quickly. It can just take the hash of the block. If it doesn't match the hash that it has, it's going to be like, no, this is the incorrect block. I'm not going to accept this block or accept this transaction because, well, it doesn't match what I currently have. So hopefully this is all starting to come full circle just a little bit. You don't have to understand this stuff super, super well, but you just have to have a general idea of why the blockchain is so secure, this concept of decentralization, and kind of how transactions get added to the blockchain and what mining actually means, right? And that's the reason why there's been a huge GPU crisis in the past and recently as well. A bunch of people are mining cryptocurrency for the incentive of trying to earn these different rewards. All right, so that is all great. And really what I just spent the last 10 or 15 minutes explaining is proof of work. So pretty much everything starting from when I started talking about blocks was trying to explain to you how proof of work works. And while that uses raw computing power, typically GPUs, to perform hashing, which then secures the blockchain in the ways that I mentioned. However, and I understand some of you may be a little frustrated here, Ethereum is actually switching over now to proof of stake. I'm not sure exactly when that's going to happen, but it's supposed to have happened for a long time, and I know it's going to happen very, very soon. And the difference is that with proof of stake, which is going to be kind of the new method and algorithm, this is a type of consensus mechanism, which is going to be used to validate the transactions versus using raw computing power. Now, proof of stake pretty much means that if you own cryptocurrency, you can stake your coins. By staking them, you're kind of putting them in a locked container. That's the way you can think of it. And what this does is give you the right as the staker of these coins to check new blocks of transactions and to add those to the blockchain. Now, I'm not going to explain proof of stake in this video. Maybe we'll explain that in another video. Point being, Ethereum is slowly switching over, or actually probably pretty quickly switching over to proof of stake, and that's going to be the new method. Now, I will just say that even though Ethereum is switching over to proof of stake, that does not mean that what I just explained to you was a waste of your time. It is still very, very valuable to understand how proof of work works, and that is currently what is being used and is being used for a lot of other cryptocurrencies as well. Proof of stake is just another method of doing this, and while I'm not going to explain that further in this video, but maybe we'll talk about that in the future. Regardless, with that said, that pretty much wraps up everything that I needed to cover. If you guys made it to the end of the video, give yourself a pat on the back. I hope that this maybe cleared up how the blockchain works and gave you at least a little bit of the insight into the theory behind it. If I were to go through and explain all of the mathematics of this, not only would I probably make a ton of mistakes, but this video would probably be 4 or 5 hours long. So really, if you can grasp the core concepts here, you have a good enough understanding to kind of proceed and to move forward and start writing smart contracts. And to be quite honest with you, you don't necessarily need to have all of this mastered to actually write a smart contract. It's just very helpful and something that I think is fundamental before moving forward. Anyways, with that said, I will finally end the video here. Thank you guys again for watching. If you enjoyed, leave a like, subscribe to the channel, and I will see you in another one.